All right, welcome! Today, we're going to tackle a really elegant shortcut in calculus. It's one of those things that, once you see it, you'll wonder how you ever lived without it. It's all about how a simple change in perspective can make a tough problem just melt away. Okay, so let's kick things off with a classic problem, finding the derivative of the cube root of x. Now, you probably have the rule memorized, but have you ever stopped to think about how you'd actually prove it from scratch? Because, if your first thought is to use the formal limit definition, well, good luck. That is a total slog through algebra with so many places to make a tiny mistake. It's the textbook way, sure, but man, is it the scenic route? But what if there's another way? A super clever backdoor that lets you skip all that messy algebra just by looking at the function's inverse. This isn't just some random trick either. It all comes down to a really beautiful, simple picture. Let's build up the intuition behind this whole idea right now. Okay, so let's just do a quick refresher on what an inverse function even looks like. If you graph a function and its inverse together, they are always perfect mirror images of each other, reflected right across that main diagonal line, y equals x. Okay, but here's where it gets really cool. That reflection doesn't just affect the curves themselves. If you pick a point on the original function and then you look at its mirror image point on the inverse, well, guess what? Their tangent lines are connected in this really neat way. And the connection? It's so simple. The slopes are just reciprocals. So if the slope on the original function is, let's say, rise over run, q over p, then the slope at that corresponding point on the inverse is just p over q. It's literally flipped. And bam, this is where the visual intuition clicks into a hard mathematical rule. The derivative of the inverse function at some point A is just 1 over the derivative of the original function. You just have to evaluate that original derivative at the right corresponding point. It's that simple reciprocal relationship we just saw. This idea is so powerful, so fundamental, that it gets its own theorem. This is what gives us the actual formula for our amazing shortcut. And here it is, the inverse function theorem. Now, I know, this formula can look a little scary at first glance, but it's saying exactly what we just saw in the graph. The derivative of the inverse is just 1 over the derivative of the original. The only tricky part is remembering you have to plug the inverse function itself into that original derivative on the bottom. Okay, so that's the theory, right? But the real magic happens when you see it in action. Let's see how this thing just demolishes our original problem. All right, let's go back to our original problem, the derivative of x to the 1/3. Step 1, what's the inverse? Easy, it's x cubed. Step 2, differentiate that inverse. The derivative of x cubed is 3x squared. Step 3, apply the theorem. We're going to do 1 over that 3x squared, but we plug our original function into it. Step 4, substitute and simplify. And just like that, you get the answer. We've just proven the power rule for a rational exponent, and it was almost effortless. And, this isn't just some one-off party trick. Applying this theorem actually blows the doors wide open on what we can do in calculus. Seriously, this theorem gives us 2 massive upgrades to our calculus toolkits. It opens up whole new categories of problems that were either way harder or maybe even impossible before. First up, like we just proved, it makes the power rule official for any fraction. You don't have to just memorize that it works for exponents like 1/2 or 2/3 anymore. Now you know why it works. It's a direct consequence of this theorem. But the second power? Wow. This one is even cooler and maybe a little mind-bending. When we use this same idea on inverse trigonometric functions, something totally unexpected happens. Just look at this. This is amazing. When we find the derivative of inverse sine, we don't get some complicated trig function back. We get a clean, purely algebraic function. The same thing happens for inverse cosine and inverse tangent. We're literally turning trigonometry into algebra just by taking a derivative. How wild is that? Okay, so let's pull back for a second. After seeing all this, what's the big picture? What's the one thing you really need to remember? Here's the deal. The inverse function theorem is way more than a formula. It's this amazing tool that uses simple geometry to give us these awesome shortcuts. It helps us prove things we already knew, like the power rule for fractions, and it unlocks brand new things, revealing these deep, surprising connections between totally different parts of math, like trig and algebra. And that just leaves us with one final thought to chew on. If looking at a function's mirror image, its inverse, can make things so much simpler, where else in math, or heck, even in other parts of life, could looking at a problem's reflection reveal a hidden, simpler way forward?